All right, hello Biochem Lab. In this video, I'm going to try to show you, or I will show you, a demonstration of the calculations that you need to do for our amino acid titration lab. So here I have the spreadsheet with this demonstration data. This is not data you should be using in your lab report. Very important to use your own data that you generated. And so here I have some made up data that will help us find an amino acid, and I'll walk you through those calculations just for the acid part of our titration, the HCl. You will also be adding in the titration data with the NaOH, but that you do in a very similar way to the way we do the HCl data. So I'm just going to show you sort of this half, and we'll go from there. So first I'm starting with your data from Table 1 and Table 2. Your titration of your unknown amino acid and your titration of water. And this is equivalent to what you would see just like we have in our procedure information. So here's the example data in your procedure that you have printed out. So here are the mils that you read on the burette started at 2 or at 5. So the first most important thing you need to do is to essentially subtract those out. So if you started with a reading of 2, this is your initial reading, so you want to make that 0. That's how many mils you added. And then just subtract 2 from all the other volume readings beyond that. So if 2 gives you 0, because you subtracted 2. 2.05 gives you 0.05, because you subtract 2. 2.15 minus 2, 0.15. So once you have those, essentially the mils added, as opposed to the mils you read, you should essentially have data that looks similar but different to the data I have here. So in Table 1, we have our titration of our amino acid with HCl, and in Table 2, we have our titration of just the water and salt solution. And the reason it's important that we measure both is we need to know the difference, right? So when we add HCl to our solution with our amino acid in it, some of those protons will go on and protonate the amino acid, but some of them are also going to go on and just protonate the water molecules or whatever else is floating around in there. So if we can calculate the difference between these two, between the solution itself and between the solution with the amino acid in it, then we'll get information that just tells us about our amino acid and not the whole amino acid in its environment. So that being said, now we're gonna go ahead and use Excel to figure out how to do that. So that's essentially using your Table 5, which is the combined HCl titration data. So the first part of Table 5 is just your information with your unknown amino acid. And so using Excel, it's convenient to use formulas and shortcuts as opposed to typing in numbers. If you're more comfortable typing in numbers and doing the math on your own, you're welcome to do that. I'm going to do my best to show you how to do this using sort of formulas, which can be quicker, and especially if you've made a mistake that might propagate through all of your calculations, it's much simpler and quicker to change that formula than to go through and fix all your math by hand. So first we're going to fill in our mils added with our amino acid, and that's just straightforwardly this column over here, right? So to copy over any cell, you'd use an equal sign, and then you click on the cell that you want to put in, and it will be the same. And then since we're going to copy all the numbers from this column, you can click on this little square in the bottom corner of our mils added in our Table 5 and drag the column down to fill in all those mils of HCl added. Same idea with our pH. We started at this pH, and then we want to drag it down to that column. So that part's pretty straightforward. The next part will require a little bit of thinking on our part. So we are trying to match up pHs with our amino acid and without our amino acid. So with the water, the solution alone. So our first pH with our amino acid is 6.98. Our first pH with our water alone is 6.71. That's pretty close. That's close enough. And so we can go ahead and put that in as a matched pH. So put this over, and then we use the equivalent mils added over here. Our next couple of pHs, 3.29 and 2.94, are pretty far from our next pH with the water added, which is 2.37. Our 2.37 pH is pretty close to our 2.5 pH that we measured with water. So we're going to go ahead and fill in that pH over here, and with the equivalent number of mils added there. And then actually the other pHs that we measured are all pretty close matches. So 1.99 close to 1.95, 1.58 close to 1.54, 0.99 close to 1.01. So you can go ahead and just drag this box down to fill in all the rest of the numbers from that column. And depending on what your data looks like, you might be able to drag everything down, or you might have some gaps in your data, such as we have here. So here we have a gap with 2 spaces. And so this might look a little bit similar but different to what we have in our procedure, where we had in our table 5, this one gap area for our pH of 5.2. We didn't have an equivalent pH for our water alone titration, and so here it was easy. There was only a gap of 1. So we just calculated the average of mils added around this gap. So we had a 0 and we had a 0.05, so we calculated the average 0.025. If you have a gap of 1, calculating the average is a pretty good shortcut for doing that, but here we have a gap of 2. So how can we fill that in? A pretty simple way to do that is to calculate them as other points on a line. So what's our formula for a line? Hopefully you remember a line is equal to y equals mx plus b, where, and in this case we're going to make x equal to the pH, and the y equals to the volume, the mils added. And the reason we're doing that is just because it sort of makes our lives easier. We're trying to fill in the gap in the mils added, and since it's a y equals kind of equation, it's nice to make y equal to the thing you're trying to solve for. You could also solve it where x and y are the opposite, where x is mils and y is pH. Just make sure that you flip everything here around appropriately as well. So the next thing to help us figure out the equation for this line is and I just also want to add, this is the opposite of the way you're going to actually graph out your titration curve, right? So our titration curve is going to look more like this, where our x-axis is actually the mils added and our y-axis is the pH. So I just want to make it clear that, what we're doing here is the sort of the opposite of that. So just keep that in mind. And like I said, you can do it the other way around. This just makes our lives easy math-wise. So the next thing we want to do here is calculate the slope. So the formula for slope, as we hopefully remember, is the difference in y values divided by the difference in x values. And here I'm going to write it as y2 minus y1 divided by x2 minus x1. So from here we can figure out our slope by using some x and y values from surrounding our gap over here. So x1, x2, y1, y2. So our x1, remember x's are pH, so we can make our x1 6.71, the value before the gap, and our x2 can be the x value. I'm sorry, I actually want to keep using our formulas here just in case, I don't want to make a typo or anything. Okay, so our x2 is going to be our x value after the gap. So that's going to be right here. Same idea for our y's. Our y's are the mils added, so our y1 can be the value before the gap up here. Our y2 can be the value after the gap down here. So now that we have these values for x's and y's, we can calculate the slope using a formula. So that's pretty straightforward. We have our y2 minus our y1 divided by our x2 minus our x1. So now we have a value for our slope. That's not a lot of significant digits. If you want to get a better, more accurate idea of what our slope is, you can simply increase the decimal places. Alright, so once we've calculated our slope, the last part that's missing from our equation from our line is the value for b. And to solve for b, we can simply rearrange this equation to isolate b. So to do that, we would subtract mx from both sides of this equation. So that would look like b equals y minus m times x. And so we already know our m, which we just calculated. And then to know which x and y to use, we just have to pick any x and y points that we know are part of our line. So in this case, we're trying to make a line that fills in our gap, so we can pick either one of these pairs of x's and y's, which we already have down here in our table. So to solve for b, we can use, let's use y2. So we have equals y2, then minus our m times our x2. And always make sure you're using the paired, so either x2 and y2 or x1 and y1. They should ideally give you the same value of b. So now that we've solved for b, we are now able to fill in the gaps for our mils added, which again is the y values for our line equation. And so to do that, we already know that y equals mx plus b. We figured out m, we figured out b, and the x values are the pHs. And the pHs that we want to use are these known pHs that we measured, that we don't have these matched mils added for. So we just make another formula over here. So in our first gap, we can have, or we're solving for y, so we have equals our m times the missing x plus our b. So that's great. And if we wanted to drag this equation, if you wanted to drag this down to fill in for the next line, we want to do that to make our lives easier, but we had to do something first, because what happens is Excel will try to increment all three of these values by 1. We only want to increment this pH value. We don't want to change our m and our b. Those are constants in our equation. So to tell Excel what something is a constant, you can add a $sign when you don't want it to change the number when you're dragging the formula through. So here we can we want to keep our m the same, which is here, and our b the same, which is here. So we add a $sign in front of that number so the number doesn't get incremented. We do want our pH to increment, so we want to leave our red one over here just by itself, no $sign. And then once we've done that, we can correctly propagate the formula. And now we have two numbers that fill in the gap between 0.00 and 0.07. And this seems good because these numbers are between 0 and 7. And if we want to look at more detail, these numbers are a little bit different from each other. And we can do that by simply adding on our decimal places here. So once you've done that, we're all set to fill in the last column in Table 5, which is the difference in mils added. And the difference in mils added is just going to be our mils added with our amino acid minus our mils without our amino acid. And again, pretty straightforward to do with the formula. So our mils added with amino acid minus without amino acid. And that formula we can just drag straight down. So now we're all set. We're ready to make a graph of our titration curve. So to get a better concept of what that's going to be, let's go look again at our picture from our PowerPoint. So right now we're kind of looking at the left half of this graph, right? We're looking at the mils of HCl that we added. And to make Excel happy, when we graph together our HCl data and our NaOH data, we're actually going to make all of our HCl's added negative numbers. So we're going to start from 0 and we're going to go negative. When we add in our NaOH data, which I'm not going to show you right now, but which you will do when you're doing your calculations, you'll keep those numbers positive and those numbers will go to the right. So right now we're looking to make a titration curve that kind of looks like this left-hand side of the graph. So our x-axis is the volume added, our y-axis is the pH that we measured, and hopefully now we can fill in some points on this graph. So let's go back to our Excel spreadsheet. So here's our data to graph. So we just talked about how our mils of HCl, which is our x-axis, is going to have to be negative numbers, but these mils we calculated are all positive. Since we started with 0, it's pretty easy just to make everything a negative number. So we just do equals negative all of these numbers. Oops, forgot to grab that last one. Great, so now we have all of our x values, and our equivalent y values are right here. These are the pHs that we measured for our amino acid. Great, so now we have our x's and we have our y's, so now it is time to make our titration curve. So if you want Excel to help you make a graph, you always want to format it just like this. You have two columns next to each other, one with x values, one with y values, and then you have the values right beneath them. You don't want gaps in between these columns or something like that because Excel will get confused. So to insert your graph, you can go over to Insert and do a chart. So we want to do a scatter plot. You can do one with connecting lines or without connecting lines. Whatever is easier for you. It's right now I'm going to show you one without connecting lines. You can try both and see what you like. I will say that when you add on your NaOH data later, it might start to look a little weird depending on where it wants to connect the lines to each other. So you might be better off just doing the dots and kind of imagining the lines filling them in. And then for any graph, we want to make sure that we have our axes labeled and the graph titled properly. So to do that, we can go into the quick layout menu here and select the first one. For our x-axis, we know that it's our moles of HCl. For our y-axis, we know that it's our measured pH, and our title of our graph can be something like titration of unknown amino acid. We don't need this legend here, we can just delete it, and now we have a pretty okay looking graph. And that can help us to sort of visualize what's going on. And again, this graph is sort of the left-hand side of our idealized titration curve, which we saw here. So we're looking at a sort of gentle slope and then a very steep slope. And that's basically what we see here. So now that we've graphed our data, we can now start thinking about filling in our table 7. So our table 7 actually has some of the numbers that you'll need to calculate. So this might help you better visualize sort of what your full titration curve is going to look like. So you start with your moles of HCl over here, your moles of NaOH going towards the right. You're looking for your equivalence points and your half equivalence points. So just to refresh everyone on what those mean, let's go back to our idealized curve over here. I will actually erase and we can begin again. So the very steep slopes on this curve, the halfway points of those are going to be your equivalence points. So you'll have one here, you'll have one here, and you'll have, theoretically, you have one kind of over here in the corner. And then when you calculate the volumes halfway between your equivalence points where the curve is sort of flat, so here you have maybe between 0 and between 8 or so right around 4-ish. That's your half equivalence point. And the pH at that value is going to be your pKa. So that's why when we look at this graph, we want to start figuring out those mil values and those pH values at those equivalence points and half equivalence points, because once we have pKa information and using our volume information, we can use that to identify our unknown amino acid. So we have, on this graph, we are showing the 2 equivalence points, so we have our other half equivalence point is somewhere over here, with our pKa somewhere around 9 or 10. So our first one that's down here, this one is the one for our carboxylic acid. And that's the one you'll see on your HCl titration. The second one, that's the higher pH, is going to be for your amino group of your amino acid. And you're going to see that one when you're adding NaOH, looking at your more basic pHs. So hopefully you can kind of keep that in mind when we are doing the math to fill out this table. So we're looking at first the initial point on the left of our graph. That's sort of the not quite equivalence point where we started, and that's going to be the very most negative number here. But in this case, we're actually looking at the volume added, not the volume difference. So we're going to take away our negative sign. So we're at 1.37, and that's mils of HCl. I'm not going to write that here, just in case we want to do some math with it, because we only want numeral values for Excel to do math. And then the equivalent pH right here is 1.01. Our first equivalence point is right up here, where our graph is the most vertical. It's going to be at our 0 point. And that'll become, ideally, hopefully more clear once you also add in your NaOH data. But for now, you can sort of imagine that this is where your graph is at its most steep, and that's at your 0 point. So that's your 0, and your pH there was 6.98. So our first half equivalence point is halfway between those two volumes, right? So you can, since one of our values is 0, you can simply divide the other value in half, but just for completeness, in case one of your values isn't 0, the way you can calculate an average is to just add together, your, to add together your two values on either side, and then divide by 2. So our volume here is 0.685, and if we want to look at our, to figure out the equivalent pH for our half equivalence point, it's, somewhere along here. We don't have, a point exactly there, right? If we look at our graph around, 0.685, which is this volume or so. We know our pH is somewhere around here. To get a more accurate value for that number, we can look at our, at our volumes added. So our volume added was we're looking for 0.685. So if we look at our differences in mils added, which are what we plotted on this graph, right, just negative, we're looking for 0.685. So that's somewhere in between these two. It's not too close to either one. So all we can really say for sure right now about our pHs at that half equivalence point is it's somewhere in between these two. If we did happen to have a volume that was exactly our half equivalence point, that's great. Then we can be much more confident about the pH at our half equivalence point. If you're unsure, you can do the same kind of idea as what we did before to calculate the equation for a line and figure out a more exact value for your pH. And if you're unsure about the identity of your amino acid at the end, you might find yourself needing to do that. I am not going to be too picky about having an exact pH here. So since we don't have an exact mils value, we can just say with confidence our pH is between 1.95 and 2.5. That's a pretty big range. And again, that's the pKa for our carboxyl group. And if you recall from looking at that table, most carboxyl groups of amino acids are going to have a pKa somewhere around there. So that's not too helpful, which is why if you're not sure about the identity of your amino acid, you might need to get more specific and calculate the value of a line in between in between the 2 points that surround that volume. So yeah, that's the beginning of table 7, and so then you'll have to fill in the rest of table 7 using the same idea. So table 7, you're going to have your second equivalence point set of data from your NaOH, and you may or may not have a third equivalence point, depending on whether or not your amino acid has an ionizable side chain. But from here, this is enough information to help us figure out the identity of our amino acid. So first we need to figure out the volume required to reach our first equivalence point. So again, that's the difference between 1.37 and 0, right, from our initial point to our first equivalence point. So that's pretty easy. The volume was 1.37. We're just subtracting 0 there. I'm not going to put units or letters or anything because Excel can't do math with that. But just know that that's mils of HCl. And then once we know how many mils of HCl we added, you can use that information to figure out how many moles of HCl that we added. So the moles of HCl, to figure to figure that out, we can use information about the concentration as well as the volume. So to figure out our moles, we need the molarity of our HCl, and then we can multiply that. By the liters of HCl, because we know that molarity equals moles divided by liters. So if we were to multiply both sides of that by liters, we could solve for moles. So moles equals molarity times liters. So based on our procedure here, we know that we have right here in our materials, we have our molarity of our HCl. It's 2 normal, and in the case of HCl, normality is equal to molarity, so we have 2 molar. So we have 2 molar times, and then our liters that we added. So here we added 1.37, and that's in mils. So if we're going to multiply by our mils, we need to convert that to liters. To convert mils to liters, we divide by 1,000. So to figure out how many moles of HCl we added, we just type that in. Excel does the math for us. So that's how many moles of HCl we added. And then to relate that to how many moles of amino acid we just changed, we just have to think about the fact that every 1 proton from our HCl went on to protonate 1 molecule of our unknown amino acid. So they're equivalent, right? The moles of HCl that you added are equivalent to the moles of amino acid that you have in your solution, because you just protonated all of your amino acid to reach that equivalent point. So if we have if we know how many moles of amino acid we have, because we know how many moles of HCl we used, and we know the mass of our amino acid, we can use that to then calculate the molar mass of our amino acid. And just to remind everyone, that's going to be in grams per mole. So we have our grams, that's just right up here at the top. We weighed that out in the lab, and then we divide by how many moles we have, which we just calculated here. So that's the molar mass of our amino acid. And that's going to be the full amino acid. It's not going to be the residue mass. There's a little paragraph about that here in the procedure. So when we're calculating our mass, we have an isolated amino acid. That's what we're working with in the lab, just individual amino acids. But sometimes when you look them up in a table, you'll actually get the residue mass, which is the mass of the amino acid when it's in a polypeptide chain. And the difference between those two masses is that they're essentially missing parts. So an isolated amino acid looks like this. When you put them all together in a chain, you're essentially doing a condensation reaction. And during that condensation reaction, you are losing a water molecule. So to calculate the difference between the isolated mass and the residue mass, you just subtract the mass of a water molecule, which is 18.02 grams per mole. So to figure out the residue mass, we subtract 18.02, which is water. So now we can ask Excel to do this for us. So we have our molar mass, our isolated mass, and then we subtract 18.02, and this is now our residue mass. So knowing this molar mass information of our unknown amino acid, now we can go to a table, our table that, you can use the table that was provided to you with the lab, and try to figure out our closest match. So we know that we're going to have 2 equivalence points, just sort of, I guess, giving that away here for this particular example that I'm giving you. We looked at 1 equivalence point. There's going to be a second there, just for the purposes of this exercise. There's not a third one. So we're looking for amino acids that don't have an ionizable side chain, and we're looking for masses that are close to 127.6. So looking through this table, what's close to 127.6? We have methionine, that's 131.2, it's kind of close, and we have our glutamine, which is 128.1. So how can we decide? We're sort of close to both. What other information can we use? So something we could do is look at the pKa of our carboxyl group, but it might not be very helpful in this case. So let's see. So for methionine, it's 2.1, and for glutamine, it's also about 2.1. So they're so close together, and before we only approximated what that half equivalence point was, right? What that pKa is. And 2.13 and 2.17 both fall in this range that we calculated. So one thing you could do at this point is calculate the line to try to get a more exact number, but to be honest, it'll be very, very difficult for you, just based on the data you gathered in this experiment, to get data to the 100th point, right? To get the difference between 2.13 and 2.17. So at this point, really, your option is just to go with the one that's closest. So in this case, the one that's closer is glutamine at 128. It's closer than methionine at 131. So from here, you can pretty confidently say that your unknown amino acid is glutamine. So hopefully that made it somewhat clear for everyone to figure out how to do all of these calculations. Again, this was just for the first half of your graph. When you add on to add in your moles of NaOH, you might have to change around. Make sure you change around the x-axis on your graph. So, but you could do like a gap here and do OH, have your HCl on the left and your NaOH on the right. Or you can just simply use text boxes by doing insert text box and just put text boxes in the correct spots on your graph with the 0 point in the middle. But other than that, I think that should be enough for you to do the math. And if anyone has any questions, please ask.